Shall we begin? Questions from yesterday? Any questions?
The concept of value
Yes.
that is it's some
Some volume.
somehow relate this quantity
I relate that quantity to something called the exchange code. Exchange code. So if you have these electrons, suppose she gets out from here, or she's sitting there. Four people say that whenever she sits here, we don't move away. That will create a void. The density of other electrons goes down.
has some value.
It has some, because this is recalculating the wave functions. It's quantitative, not qualitative. If I put in the values of y, y, I, that, that at each point it's more than qualitative, it's quantitative. Calculate exchange energy component, right? Not calculate the exchange energy if it's not quantitative. Does that answer your question?
If the value of and the value is something one or
Oh, that integrates to one. Integrates to one. No matter what the value is at different points, it always integrates to one because otherwise the probability would not be normalized. Anything else? Yes. Louder. So there are two I have wrote very clearly. The first one that I calculated, which was the Fermi hole, right? There was no interaction. This was even for non-interacting. That was coming because parallel spin electrons avoid each other. That's nature, Pauli exclusion principle. If you really want to think about it, the way I think about it is each one has a delta function, wave function, and two cannot have the same wave functions throughout. Parallel spin is not. That's because of Pauli exclusion. Furthermore, by adding interaction, they go further out. Effect on parallel would not be that much as would be on the anti-parallel because they can come close to each other, right? But parallel obviously they go a little further out. Just so that creates another hole. That creates another deficit around each electron. That is due to Coulomb interaction. Total thing I'll call exchange combination. Does that answer your question? Any else? Okay, so now we'll get more sophisticated today after this discussion. And so let me start with the Hartree-Fock equation. Oh,
in the board. What?
oh yeah, okay. No, I'm looking at the thing. Then, hello, good morning, everyone. Arun Kantoli, Soumya Gorai, Madhurita Das, and Manodev Ruth. Are you related to that Ruthenian Ruth? Raut, huh? Okay. Yeah, this is like Yadav becomes Yadav. Okay, so what we're going to do, I'll start with Hartree-Fock equation, right? Analyze it. I'm spending so much time on Hartree and Hartree-Fock because that's precisely what we're going to do in density function theory with a qualitative difference. If you understand all these equations well, you will be doing well there. And that adds much more because that gives you a variable which is density. Formalism becomes roughly the same. Other thing is, as we talked about yesterday, getting a wave function which is fully interacting exact wave function is impossible. You do not have a computer with that kind of memory, right? So we necessarily do this, and the simplest is start with mean field. And then if mean field is good enough, you can build up upon it. Hartree-Fock happens to be a very good mean field. Qualitatively, there are some problems. Those we'll correct, but then you ought to know which way. Okay? All right. So now, if you look at Hartree-Fock equation, I want to write in a particular way. The way is that we wrote minus 1/2 del square plus B external R plus B Hartree, all well-known terms, and this new animal called we exchange, and we said we exchange R prime phi I R prime dr prime, right? And this fellow acts locally equals epsilon I phi I. Again, the question that we talked about yesterday, I am minimizing the energy with the, these are known as canonical Hartree-Fock equation with only orthogonality condition. Orthogonality is not taken, if epsilon ij are taken, you can also diagonalize it, but right now we're just doing this. Okay. Now, the certain properties. So again, if I calculate the energy, which is going to be a functional of psi Hartree-Fock, is going to be the kinetic energy, right? Which will be summation I phi I of del square phi I. There's also a spin of sum, unless otherwise specified, where really makes a difference, I'll say. Then I'm going to have integral P external R rho R plus E Hartree, which is 1/2 rho R prime over R minus R prime dr prime plus E exchange, which is nothing but minus 1/2 integral rho exchange. You see, introducing that good idea, rho R over R minus R prime dr prime. I could write plus if I take rho x to be minus, but that's my convention. So this is the energy, which can also be written as summation I epsilon I plus other terms. Left as this. Good thing about being about a lecturer is whatever you find boring and you can leave it aside. So I've done it many times. You do it. So anyway, this is the, and notice I'm writing this as a function, right? So there are certain properties, and this B exchange I won't write because I'll spend some time on it. The exchange R prime, is I've written a plus sign, I'll write the minus here. It's going to be minus summation j, and this depends on the spin. If it is for ms, it's going to be yj star r prime yj r for the same spin over r minus r prime. This is j occupied. Right? That's all. Now, there are certain properties of this. Does this energy alone is good enough, or can it give me something more? Right? So, to motivate that something more, what I'm going to do, suppose I have a non-interacting system. There are these orbitals, epsilon 1, epsilon 2, epsilon 3, epsilon 4, and so on, and this is my zero of energy. Right? Non-interacting, nothing happens. So if I remove an electron, so if I remove a particle from here, energy required is going to be minus epsilon 3, right? And that's going to be removal energy. In a non-interacting system, right? Can I do something similar in Hartree-Fock? Although it's a interacting system, but after all, it is giving me orbitals, right? Hartree-Fock, I'm getting the orbitals. Obviously, if I go to an extended system, they become continuous. But for the time being, let's write E epsilon Hartree-Fock, E2 epsilon Hartree-Fock, and so on. And here is my energy zero. If I remove an electron in Hartree-Fock here, right? If I remove an electron, what happens? The density is going to change. One of the orbitals will go away from here. All these potentials are going to change. And therefore, if I solve this self-consistently again, everything will change, right? But you can show that change is going to be very small. So I have something wrong. So epsilon is going to change. Ideally, you should be calculating the ionization energy by subtracting the two energies. So if I were to calculate I Hartley form, it will be E Hartley form or n minus 1 particles minus E Hartley form or n particles. Is that okay? That will be the exact answer. But who wants to do two calculations? So what you do is you have something called the coupon system. It's not Koopman's theorem, it's Koopman's. His name is Koopman's. It says that removal energy is approximately equal to minus epsilon r from r. So you calculate this difference and you find a little bit, difference is there, but these are good enough. So now that I've said this, right, which one do you think, if I calculate it this way, I Hartley Fock this way, and I say removal energy, right, this way, which one would be larger? So Koopman's theorem is all right? Suppose the removal energy is 5 electron volts. Would Koopman's theorem tend to give me 5.01 or 4.99? Think, I'll give you time. The question is also open to people online. Question is, if I calculate removal energy by subtracting the two energies or by Koopman's theorem, why is the board ulta out here?
It's showing.
Was showing okay. Right. So left, right is okay. This one is okay. This is like standing like this. All right. Which one would be higher? So if I have the exact answer, epsilon n minus 1 minus E minus 1 minus En equals 5 electron volts, would the Koopman's theorem give me 5.01 or 4.99? सोचो और बताओ. If you understood the variational procedure, if you understood everything, you will. And reason has to be there. It cannot be it feels. Okay, I'll wait for some time.
So you are basically measuring the same quantity, so answer will be the same.
No. I said this is theorem, and I have put this because if I do remove an electron, all these quantities change. If I do a calculation for n minus 1 electron, my potential has changed a bit, right? So my epsilons will change. All right. So it need not be that this should be equal to. So all one is saying by Koopman's theorem is that I E n minus 1 Hartley Fock minus E n Hartley Fock is approximately equal to minus EI Hartley Fock. It need not be. So does that answer your question? I mean, because I'm changing the potentials when I remove an electron. Yes.
We get higher energy from Koopman's theorem.
5.01 or 4.99?
5.0.
Why?
Because the radiation principle always measure the ground state, which is new. So this energy will be lower than Koopman's theorem because Koopman's theorem is
Not relaxing the orbits. Very good. So what he says is this number would come out to be slightly larger because when we did self-consistent, this is nothing but a manifestation of self-consistent principle. We minimize the energy, that's how we got the equation. So En minus 1 here would be slightly smaller than if I did not relax. Right? Whereas when I calculate it this way, I'm assuming nothing is getting relaxed. So that's a very good answer. Anybody has any dispute with that?
and also because we are like moving one at a time, we're going lower in energy.
No, higher. That's negative. Ionization potential is positive.
You're putting, removing.
Yeah, if you remove, you require some negatives, right?
Oh, you're adding
It's,
a
you're less negative. Less
You're
negative.
adding-
You're confusing with the negative. You're adding. It becomes less. Okay? Alright. That's Koopman's theorem. That's number one. Then there is Brillouin's theorem. So, after all, this is an approximate wave function. This has only n orbitals, whereas in reality, two wave function, right? Psi 2 R1 R2 would be a sum of Ck psi R3 for k. That means the excited states also. We'll talk about how you get those excited states, but nonetheless, that's what it's going to be. What Brillouin's theorem says is that if I replace only one orbital, that is, I take psi Hartree Fock ground and psi Hartree Fock, where say IF1 has been replaced by some alpha F1 unoccupied. These were the orbitals, occupied orbitals, and here's an unoccupied orbital alpha. If I replace one of them by that, right, the delta E is 0. So you got to replace at least two orbitals. That makes sense. Replacing one orbital means you're doing first order perturbation theory. You're calculating first order change. But you minimize the energy. So first order change has to be 0. That's the simplest way of looking at it. So minimum change you need is a second order change. So you have to replace two. That's Brillouin's theorem. All right. Number 3. Band gaps in HF theory are much larger than true gaps. Okay, now we are coming to the field. Okay, so if you have like 3 electron volt band gap, you will get 5 or 6 electron volts. Okay, let's understand why that happens. And that will also tell you how to calculate the size. HFT. Okay, so why that happens is I'll leave this equation here. So remember, all this equation has been solved by calculating everything up to the occupied levels. At 1, 2, 3, 4, and here are the unoccupied levels. This is the gap. So if I were to do a band theory, this will be the valence band, this will be the conduction band, right? Now, how do I calculate the upper band in this, upper levels? Any ideas now that we're solving the equation? How do we calculate the unoccupied levels? Bolo, could be Bolo. I want you to think so that even if the answer doesn't come, you're at least halfway through. How would I calculate the upper levels? Because all these potentials are coming from the occupied levels, right? I'll do the same thing. I'll keep this fixed from the occupied levels. This is fixed, this is fixed, this is fixed. Whatever density I calculate, this is also fixed. All I'm doing is, instead of I, I'm writing now minus 1/2 del square plus V external R plus V Hartree, all calculated from occupied levels, right? Plus this on I alpha, alpha is unoccupied, plus integration Vx R prime y alpha R prime d R prime equals epsilon alpha. phi alpha. Okay, and this gap is epsilon alpha minus epsilon whatever 4. Okay, is that okay? And gap anyway, things don't change much. There's an infinite system, so a little bit here and there. So now look at this. Vx r prime. This is equal to minus summation over j occupied. There's an ms also, so we're doing the same. J ms r star by j ms r prime here, r minus r prime. That's it, right? I'll do one trick. I'll add alpha to this. So I'll write this as summation j plus alpha. Okay, yj ms r prime star yj r over r minus r prime. Let me write this thing. Minus phi alpha star r prime phi alpha r over r. So, is that okay? I've added this and then I subtract this also. Plus same thing. Alpha p alpha. Is that okay? Now, yes.
You have just changed the indices. So how do you visualize unoccupied? There is no.
So I'm putting one particular spin. I assume that orbital has the same spin as ms. Right? Whatever. I mean, I can put any spin I like. Right? There are two of them. Right? So a particular ms. So I'll just write ms. Because lower ones I'm assuming W occupied, fully occupied currents.
Yeah. So basically, you are adding like a density from the even the higher extent state.
Right.
And basically,
Yeah.
you are calculating.
Yes.
And what is this V alpha?
V alpha is the same thing. I'm just writing this.
Oh.
So I didn't want to write again, but I'm going to write now that you said it should be noted. Alpha y alpha r star ms over r minus. That's why I wrote that V in a particular form. Okay, this way. Now let's change color. I can stick on the same color. Okay. So this part now, how do I calculate the exchange part? I calculate by integration px r prime y alpha r prime dr prime, right? So this will become summation, now I'll write j plus alpha. This whole thing I'm calling j plus alpha yj I equals j plus alpha, right? I r prime star ms y I r over r minus r prime y alpha r prime integration over dr prime plus this. Plus, when I do r prime integral, that gives me 1. Right? This gives me integration y alpha r prime mod square, because this and this give me that mod square over r minus r prime dr prime, and I can write this as final. Let me see. I've gone over this. Let me see if there are any questions. Are the steps clear?
Third step, last one.
Here, this one. This was I was occupied doing only occupied case, right? I've just added whichever higher orbital I want to do. I've added that Vx part of that. That's all. Added and subtracted. So I've added 0. But now when I do the integration, I'm including that j plus alpha in this. I is up to j plus alpha. And this part has to be like this. This is the Hartley potential due to alpha. Right? So now, in fact, what I'm solving is this equation. I'm solving the equation minus one I'm solving for alpha, not others. Del square plus V external, that part remains the same, plus V Hartree n plus 1, because I'll include that in that Hartree. There is a Hartree term. Plus V exchange n plus 1 R prime, Y alpha R prime, P R prime, Y alpha is equal to epsilon alpha phi. Is that clear? In effect, I have added and subtracted the self-interaction of the alpha as well. Right? But look at this equation. This is as if I'm solving an n plus 1 particle problem. I'm solving an n plus 1 electron particle problem. The orbital phi alpha that I'm calculating for the upper one, in effect, is as if there were these orbitals, and there's one electron here also. Isn't it? If you look at that equation. Is that point clear? Or are there any doubts on this? If I'm solving the n plus 1 electron problem, is the interaction potential little larger or little less? Instead of n particle, larger. What will happen to the eigenvalues? They'll get pushed out. That's it. What should have been for the n particle problem actually is for the n plus 1. When you're calculating the gap, E gap, you're calculating epsilon Hartree Fock for n plus 1 minus epsilon Hartree Fock for n particle, which will necessarily be greater than E2 n plus 1 minus E. That Coulomb interaction. Therefore, Hartree Fock gaps always come out to be larger than. If you look at any PRB that have done Hartree Fock calculations, you pick up, look at the gaps, you find there's no exception. Is that point clear? Any questions?
Previously, you were showing that there is self-interaction energy and also exchange coordination. Is self-interaction energy a small part of exchange coordination? Because in both cases,
So we have, since we wrote Hartree by including self-interaction in it, right? So I have to subtract this. That's why exchange hole is 1, is that self part.
it is equivalent to self-interaction. This exchange coordination.
Exchange coordination is self-interaction more. Self-interaction would be only this part. Orbital interacting with itself. When you write this exchange term like this, it is other electrons also interacting. Does that answer the question? Anything else? Okay.
So here, like we are adding this one extra electron. So
Yeah, it is as if you are adding.
as if. So basically, then we were counting the.
That's right. That's why the gap is high.
Instead of easily just subtracted the electron, like
That would be upper level. Upper level. That would be exactly level.
but then even for doing that, you've just taken out the electrons from the occupied.
No, but if I want to find the gap, I
So
don't
I'm
touch this,
expecting
right?
that electron from occupied to
unoccupied.
so then the
But then you're not calculating the gap, you're actually calculating the excited state.
oh and so you also wants to
So I'm in your language, if I take the n electrons and I take n prime orbitals and diagonalize, I'll be getting n prime orbitals, right? So the lowest unoccupied and highest occupied gap will be the gap. That would be larger. I'm showing this. So because you will be getting all this if you take the basis set calculation. This will necessarily be much larger than that.
yeah.
Okay? This is something not many people will tell you. So please understand that. Pick up PRB, check it, whether I'm right or wrong. Okay, pick up Hartley, just type on Google Hartley for gaps. They'll give you a lot of PRBs. Okay, so that's one thing about Hartley. Gaps will always be larger. This is very important because when you do cone shaft, it will be slightly different. Now, other things that Hartley Fock fails, if you look at metals, right? You look at metals. Free electron theory, which is otherwise known as Sommerfeld model. Works well. Right? You after all, Norman has the fifth chapter, Pickle has sixth chapter. They're all devoted and you went experiment beautiful. What happened to the electron interaction? Why do you think free electron theory is working well? Again, I'm spending time on this because these are very important concepts for any anybody field. Cone shaft or no cone shaft or DFT or DFT, everything has to be followed. Why do you think this happens? Think about it. Okay? If you do Hartley Fock, results go haywire. Occupied gap, occupied band becomes very large. The when I say it works well, it works beautifully because it gives you CV proportional to T, right? Whereas if you do Hartley Fock, C V Hartley Fock comes out to be proportional to T log T. I may be a little wrong here, but that's what it comes out to be. It's a logarithmic dependence. It's all crazy. Hartley Fock fails. Big time. Alright? It's not T log T, it's go to 0. I think it's log T. Why do you think this happens? Why do you think free electron theory works well? Also, जो मनी इलेक्ट्रॉन थ्योरी कर रहे हो answers. Say something.
So here you are showing the gap, but for metal there will be no gap between valence band and conduction band.
Yeah, so I can strip. So here's the conduction band. I can do Hartley Fock with all this. This gap comes out to be too large, and this CV goes as log T.
And that gap will not exist for the conductor and metal.
What?
That gap you are showing here,
What gap?
the gap between four.
No, that's fine. So Hartley Fock is done for occupied levels, right? भूल जाओ उसको भी, हो गया ना? All that is done.
maybe the
How?
kinetic energy is more than the potential.
Huh?
Kinetic energy is more than the potential. That means the difference.
Kinetic energy is more than no. Electron interaction is. And in any case, in this case, things are spread out. Okay? Good try. Right? Even your answer is a good thing because every time, even if something is come up, when we discuss, we learn a lot of things, even if the starting point is wrong. It's the screening. Moving electrons screen each other. Effectively, they're not interacting. Effectively, each electron is moving freely because its charge is screened by the other. That's consistent. In fact, what happens now physically, what happens is if there are these long-term interactions, right? All these electrons get correlated, they move together, they give you something called the plasma oscillation. And short-term remains. Short-term means there's hardly any interaction. Short range. Long range gives you this collective oscillation of the whole. That requires a lot of metal. That part is not excited. So now, if you want to do proper theory, you'll have to include correlations. So if you have to pull many electron theory, I'll get a good answer. Or if right from the beginning I say I'll model it like free electrons because the interaction remaining is a short range.
In the exchange correlation, already the correlation is taken. Or the electron is
No, right now I'm doing Hartley form.
the Hartley we are getting the wrong from the top T, and in the Hartley we also implement the correlation.
No, only Pauli exclusion principle, no Coulomb. Wave function is still right. It's done in a mean field way, right? That was there any other point I want to make about Hartley form? Then grab Blois theorem, Pouffan's theorem. So now let's quickly inching it towards GFT. So this is this. Now I'll focus on metals because that's why strategically I said metals. What I'll call technically what is known as the homogeneous electron gas. And this becomes the paradigm for doing DFT to start with. Okay? Homogeneous electron gas, I'm assuming homogeneous positive background. And electrons are moving in. Obviously, the charge is neutral. Alright? So, you're doing minus 1/2 that is square plus V external, whatever V external is, plus V hard 3. And the two cancel. Show you in a minute, but anyway, let's write this. V external, which is due to this all positive background, plus V hard 3 plus phi I plus V exchange R prime phi I R prime equals epsilon I phi I. Okay. Now you can show that self-consistent results. What I'm now specializing to this, okay, will be plane waves. So still I free electron here. Why? What does plane wave give you? It gives you a density which is fill in the gap. It's constant, uniform. That since charges are the same, that density would be the same as the positive charge density. So the potential you have for each electron will be positive, exactly negative of this, they will cancel. Alright? Similarly, if you calculate with this, the exchange correlation potential, alright, it comes out to be a constant. So plane waves are the same. Does that make sense? So automatically I've argued they're going to be plane waves are the solutions which are self-consistent, so these are going to be the solutions. Now, beauty is that in this case we can write a lot of things in the
Even if we consider free electron theory with the Brownian motion, then we have not to consider any self-interaction energy.
How does the Brownian motion arise?
In Brownian motion, there are gas particles.
Yes.
And they randomly move.
Right? Why do they move randomly?
There is a energy supplied by the temperature.
If energy is supplied by the temperature, why do they become random? What makes it random?
Because there is not any particular field, so it does not go.
There's no field, right? But why does it become random? Why is this particle going and suddenly says I will go like this and the larger velocity?
But they are colliding with each other.
What does collision mean in terms of physics? Interaction. Interacting with each other. I've already taken interaction.
don't think in terms of the temperature. When there's a random motion,
Random is because
random motion is going to, if it is complete solid, zero temperature, it's going to move into its potential created. Right? So there's no randomness there. Only after.
They call it the binary theory of this.
yeah, so they are colliding, they are interacting. I've completely taken that into account. So you should also ask me where is this leading? Come automatically because I've taken the Hamiltonian, which is complete. Solving for the complete wave function. Everything is built in. All these things are done when you do approximation. So I'll throw in staining, I'll throw in randomness. I don't have to do that. I'm solving the exact equation. Right? Does that answer your question?
So he had a picture of group model in his desk. Group model is something which is at very high temperature. Everything is sort of what kinetic energy we are talking about, that's generated because of your no temperature, nothing.
Got it. Anything else? Okay. Now, if this is the thing, I can calculate the kinetic energy. Always motion plus Celsius, this has to be filled up to a certain level. So this is pi I minus r del square pi I summed over I, and you can show this comes out to be 3/10 3 pi square is to 2/3 whole is to 5. Yeah, right there, yeah. F square, F square. So just I mean, there will be some factor here. If I don't remember it correctly, it will be some ck, right? Rho raised to 5. Constant density is constant, doesn't matter. Similarly, V Ex or E, let's calculate E V external will be integration V external rho R, rho is rho, dr, and E Hartree would be, this is the minus sign because V external is with a minus sign. This is the same density as the electron, so it will become rho R prime if you like, write it symbolically, the minus sign, and this will be plus rho R prime over R minus R prime. dr prime, there's a half, there's a minus sign, they cancel. And you get E exchange, which is integral, let me write this 3kf or 2 pi rho dr, so this is proportional to integration rho raised to 4/3 times the volume. This is integration. Right, where kf is defined as this is orbital 3 pi square rho raised to 1. Okay? That in terms of kf is easy to remember. I'm going to write this as 3/5 mt. So exchange is known, that part cancels. So total energy is only the kinetic plus exchange, and this is written very nicely as energy per electron 1.105 over Rs square minus 0.456 over Rs, where Rs is defined as 1 over 4 pi by 3 Rs cubed equals the density. That's like the sphere in which one electrons. That's Hartree-Fock. All right? I'll just give you an assignment problem here. Show that in Hartree-Fock theory, ferromagnetic state will be more stable than paramagnetic state for after crossing certain arms. Do you understand the problem? That means if I cross a certain RS, I'm not even telling you whether it's going below that or above that. All electrons will be parallel rather than parallel. Parallel anti-parallel is paramagnetic state, that means it. Alright? Because there will be a factor of 2/3, 2:1/3, 2:2/3 in calculating this, and leave it there. Alright? So that's this. This is it. Now, once you do this,
And your temperature is changing, like cooling temperature.
zero temperature. Zero. No ground state. During ground state.
But during phase transition, TC is equal.
No. I'm not doing any phase transition. I'm saying if you are below or above certain RS, energy of ferromagnetic state would be lower than that of paramagnetic state. Okay? Now you have to keep in mind that if I have these orbitals, in a ferromagnetic state, you'll go up to much higher levels if you're filling only one electron. Right? But even then it will be. Alright? So that's RT form. Now, can I do something nice out here? This is as far as RT form goes. Now, just a quick calculation about estimating correlation energy in a certain limit. This is the energy. So the picture is that you have this metal. I'm assuming that each one has this sphere of radius Rs, and one electron has this much, right? Making this picture with something in mind. Now, there's a concept called Wigner crystal. Which is if you go to very low density, right? Low density means RS is becoming large, right? RS is becoming large. Electrons freeze into VCC. Although VCC, but crystal is more important. So you would have these electrons sitting, and there's a sphere of positive charge. Okay. If that's the case, now E Hartley fog in this case would still be 1.105 over RS square minus 0.456 over RS. If RS is becoming very large, this term is much smaller than this, right? So this you can show. Limit RS tends to infinity. This goes to minus 0.456 over RS. Agreed? Whereas now in this limit, these guys are frozen within this positive charge sphere. Right? So I can calculate the exact energy. Isn't it? I know the potential at the center of the sphere. Right? So if I calculate the exact energy per electron can be calculated in this case. How do you do it? You would say per electron each is frozen here in a sphere of radius r. So you calculate the energy of the positive background, calculate the interaction energy between the electron and this. That gives you the total energy. Right? What will that be? E per n would be potential of this at the center. 3/2 is exactly one charge. 1 over Rs. So the energy would be electron interacting with this will be minus 3 by 2 Rs. And the positive energy of this is plus 3/5 Rs. This plain electromagnetic here. Coulomb's law. That gives you minus 0.9 ohms. That's the total energy. And by definition, now I'll come here. By definition, E correlation is equal to E true minus E Hartley fog. Whatever is you're going beyond Hartley fog is correlation energy. That's coming because of the fact. So in this case, limit Rs tends to infinity, E correlation is this minus this. You can say this is minus 0.4. Is that okay? Is the point clear? I'll wait here for some questions. Now we are really getting into heavy stuff. Any questions on this? Anybody from the other side? Mandeep Raut, Arun Kantoli, Madhurita Das, Yango Nikhil, you have any questions? Sumani Patra, Shivam Jani. Okay. Yes, Shivam, ask me a question. You said yes.
Unmute and then you should unmute.
Please unmute.
Yes, there is a message.
No, sir, no question. Okay. And if I can be little Bollywood like, okay, Johnny. Okay. So, any questions on this? Now, what do you think happens if density, instead of being so low, I start increasing it? What will happen to the correlation energy? Relatively, will it increase or will it decrease? Why does it form? Okay, because that's the most stable energy form. That's the simplest answer. But as you go far away, right? Kinetic energy by uncertain distance starts going down. They can't really move much. So now the only thing that is happening is the Coulomb interaction, the long range interaction. It affects even if they are very far off. And that Coulomb interaction, best possible choice to minimize the Coulomb energy is to be finite. Okay?
You don't feel the exchange correlation value more slightly higher. Because for the free electron, we will have nothing.
No, correlation is there.
Correlation is there, but the value is so low. That's why we can assume that.
No, relatively it's low.
But here also we are what we are assuming.
It's much relatively it's low.
But here we are assuming radius is extended till infinity.
Yes.
That means the sphere, like the smearing is also there. The other spheres.
Yes.
That means we should place value. Here we can.
That's the question I'm asking. Would correlation be relatively larger or smaller? Relatively larger, smaller if you go to lower density. Why? Not, you knew I was going to say ask why. Number देखो तो बताइए मुझे why. And I gave answer when I was answering for him. When you go to larger distances, kinetic energy goes as 1 over distance square. Coulomb goes as 1 over distance. Coulomb starts dominating. Coulomb dominates, correlation energy goes higher. Exchange is anyway is going to be low because you're very far off.
In the metallic metals,
Yes.
and also metals means we have the low correlation. Electrons, so many electrons are there.
Relatively low. Relatively is important because kinetic energy becomes very high. In the case of far off, kinetic energy is almost going to just going down much faster. It's going as 1 over distance square. It's all relative.
In the metallic situation, kinetic energy is important or the correlation is important.
Depending on the property. Correlation is important, is less important.
What is this? Kinetic energy.
If I'm saying kinetic energy is much higher in metal, what will be more important?
That's like the first answer when you ask the reason metal, the like the correlation you ask, what is the reason they don't have any interaction? I told you that the kinetic energy is the reason. And you told me that there are squarings are there are correlations are there. Correlation is low.
You are upset about that?
No, I am not upset. I am just trying to understand.
What, what it is there are a lot of electrons. Correlation is still there. Energy is going, they are all correlated, so it's going into collective motion. It gives you something called the plasma oscillation. And lower energy doesn't matter. That plasma thing doesn't get excited. So they're moving freely around. It's like if you're in low energy, it can pass around. Right? But your interaction energy, you need much more moving to excite everybody. Right? So long range part of the Coulomb correlation actually goes into that collective motion, which is much more difficult to excite. That kinetic energy and all that is moving around like free particles. There's a short range. That is left.
That means the kinetic energy is short range, but Coulomb interaction is
Absolutely. Our kinetic energy goes as 1 over distance square. Short range is much more effective. If you are confined to short range, the kinetic energy becomes much more effective. And there's a kinetic part of plasma also, is an oscillation.
those two kinetic energies are different.
Finally, if you calculate the true energy, the sum of everything, right? What you're doing is you're kind of decoupling the two kinds of motions. You want to calculate true energy, it will be that plasma part plus this. So let me just give you what I'm saying. I have this Hamiltonian, which is minus 1/2 del square per da. You separate it into two. One, an oscillator like plus one Hamiltonian with short range. And there will be a coupling term which you can say is very small. Then the true motion would be wave function for this, which is that collective motion plus this. For low energy, this can be ignored. Maybe there in the ground state.
The oscillations are coming correlated.
Because of the Coulomb interaction, yes, correlation among each other. All the electrons are correlated. Collective oscillation would not take place if only two are. Just like in this group, I tie each one of your hands to the other person, right? And if you want to move everybody, you need a lot of energy. But if you're moving around here and there, it's fine. Right? That's free electron model if you're just moving around here. Now take the whole thing, that's plasma. Is that okay? Anything else? Okay. Now, so correlation energy relatively would be larger if you go to larger density. Small. So this is RS tending to infinity. For other RSS, you can do an interpolation formula, which is minus 0 point some number, maybe 444 or some other number, divided by RS plus some other number. Okay, this is known as Wigner interpolation. This is one of the earliest approximation to correlation. There are other ways of doing correlation energy. Is not, now you realize it's not as easy to calculate as exchange, which you could calculate exactly. even for homogeneous electron gas. Okay. Now, other thing is you can do a high density limit. This is the low density limit, right? You can do a high density limit. That's a real tough calculation done by Hillman and Bruckner. That gives you a RS log RS limit. Very short RS. Okay. And then you interpolate. You also, if you want to produce a formula, even for homogeneous electron gas, then there are Monte Carlo calculations. One of the most famous ones is separately ordered calculation. Just give you this. Just type it in. Separately ordered. Here. So this gives you a range of RS. This is Monte Carlo calculation. And you know the high density limit, small RS limit. That's Gell-Mann-Russell calculation. You know the low density limit, you interpolate. You produce these interpolation forms. There's no analytical form. You have to generate it. Is that okay? So, just to summarize this whole thing, can I erase this? By the way, if somebody is taking good notes, like a copy of it because more than 50% of it is impromptu. So I don't have a systematic.
Any of you are taking that? That will be great. Actually, we will keep it on the website.
Now,
Yeah. Anyway, video lecture will be there.
so the question is that what we have done, just to summarize, I did Hartley Fock. All right, we got kinetic energy, which is one particle, 1.105 over RS square. Exchange energy, one particle is minus 0.456 over RS. And I would just say, by interpolation, E correlation, we say call this bigger formula for n is minus sum A over RS. Okay, just keep this in mind. Then this implies that total energy Ke for n particles comes out to be some Ck integral rho raised to 5/3 times the volume times the number times the volume, because n is 3 pi square rho raised to 2/3. Right? This is nothing. No, this is n is rho. This is rho raised to 2/3. So that's what it comes out to be. Exchange energy for n particles, we come out to be some C exchange. The minus sign of C exchange would be minus rho raised to 4/3. B. Correlation energy will be integral A over RS plus B times rho times A could be negative. Negative if A is positive or minus. You put minus here explicitly, so it's clearly a negative. Okay? That's where we say this is homogeneous. Now the question is, this is in terms of density. This is in terms of density. This is in terms of density. In general, I know E external. So this is homogeneous. We draw a line here. For others, I know E external integral E external R rho R B R. E Hartree is integration 1/2 rho R prime over R minus R prime dr prime. Right? I have all the terms which are in terms of rho. can I do an approximate calculation in terms of the density? That is the next question. Right? The easiest thing would be to do is this. For an inhomogeneous electron gas, where the density is rho dependent on the position, right? E approximate can be written as Ck. Instead of V, I'll integrate over the volume because at each element I'm taking this plus E external plus E Hartree plus E exchange minus Cx integral rho R raised to 4/3 dr plus E correlation. So let's just write this A over Rs plus B. There could be other forms, but I'm just taking this. So R, yeah. This also depends on R, right? Rs will be. What is Rs from here? Rs is 3 over 4 pi rho raised to 1/3. Let's write that. 3 over 4 pi rho raised to 1/3 rho RdR. And it's approximate, I'll replace by this is approximate. Since I'm anyway doing an approximate calculation in terms of wave function, anyway getting approximate answers, why not make it easy? Why not do it? I have all the expressions from it, so let's try this and see what answer we get. Much easier than solving all those, for each orbital, for each everything, right? And how would I generate the equation? So this is the energy I have written. I have written the energy, the equation for the density. How do I calculate the equation for get the equation for the density? The ideas? This is given a density, it gives me a number, so it's a function of so what is my variable now? Huh? Density. I minimize with respect to the variable. Get my equation. Right? So yeah, I do, and this is a functional, so I'll do functional derivative. It's better to write this as r prime, doesn't matter. So that r prime, r double prime, r prime, r double prime, r prime, so that when I take this to r, it's with of E approximate. We understand it's approximate. Rho minus, I need a Lagrange multiplier because I have to satisfy certain condition. What will be the condition? Number of particles. integration rho r prime dr prime minus n. Yes, this method will give you only the ground state. You have a better method of finding the ground state, do that. So far we have enough. Right now we are just focusing on ground state. But Hartley Fock was also only ground state. Okay? Thing is, even finding the ground state is very difficult. And fortunately for us, electrons obey Pauli exclusion principle. So unless you are really at 10,000 degrees, okay, room temperature comes. From that itself you can make out. Okay? There's another way of looking at it. Why should so it gives you delta E rho over delta rho r. Yesterday I told you how to find functional derivatives. I need not go over that. Minus mu equals 0. Another way of looking at it is, what do you want? So this is a very physical way of looking at it. Delta E is nothing but delta E, delta rho r, delta rho r dr. By definition of functional derivative. Now this, what is this integral? Always 0. We are not changing the number of particles. So you can vary delta, vary rho, but this integral will remain 0. If it has to remain 0, you can make this a constant, still the delta E will vanish. 0 with condition that delta rho r dr is equal to 0 implies delta E delta rho r equals constant. Otherwise, if that condition was not there, this has to be 0. You put a condition here, you relax the condition. That's how you do it. Okay, where mu is the Lagrange. This is the equation for the density, which now would become
Sir,
yes.
you can choose this is also good, like the delta E, like the derivative is also getting a 0 now. The constant, we can also think about this as 0.
Yes,
It's
it could very well be 0, yes, but a priori I cannot say 0.
like feel like for the thinking purpose, we are varying rho values and calculating the ground state energy value. For a certain ground state, like
Why do you want to put a stringent condition when it is relaxing? It is saying it is giving you the freedom.
giving a freedom, but
You want to say no, 0
no, because what I
if mu finally comes out to be 0, that's fine. Mathematically, I cannot put it 0 right from the beginning. I cannot assume.
if we assume like if we think like this, we're varying rho values,
Yes,
and in the y coding we have the e values.
yes,
For a certain rho value, we are going to get the ground speed
Yes.
and the minimum value of e.
Yes.
That means the derivative over this daily lil rho is always 0.
no. Delta E is 0. Not derivative. Change in E is 0. That doesn't mean derivative is 0. Rho, symbolically, E, right? This is rho 0. This is E0, right? You go to density here, right? Let me just make it schematically a little bigger. This is rho 0 plus delta rho. This is rho 0 minus delta rho. Symbolically, this changes, not the derivative, but still be constant. That's why I said you're getting a more relaxed condition.
That is
I'm telling you, go from here to Lucknow. You're saying I'll go to Delhi, then maybe New York, like that. Yeah. Yes. I could expect, but what is my variable? What is my variable? Huh? What should I minimize it to? Huh? Mu. How how does mu become variable to start with? And I had this energy expression. And I had this energy expression. What do I minimize it with? That's what I'm doing. Why should I confuse myself? Thinking ahead. Just because I know the answer, I should not confuse myself. If I just look at this, what would I do? What is my variable? There is no mu here. Mu fixes the number of electrons. Right? Okay. So I've derived the equation. So it's better to write it like this. Because I'll interpret this. Take a short break. So we start from here.
So we have a keynote, right? Let's go. So again, within 15 minutes, we should be back. Okay. So we have online people. We have a short break for 15 minutes, and we are going to meet soon. You can also have tea, coffee, or even
Maybe a
water.
nap. If you haven't had one already. Oh, so on this it is left right, and on the laptop it's up down.
Down is no. It's like left right.
This is what down from.
No, no, no. Left right.
Does anybody have Google? देखो 1 hour of it उसमें कितना कैलोरी जाता है, हम यूज करें 1 hour of lecture. Accordingly, today I had 2 points also. Maybe useful for some of you also. Maybe lecturing is not important.
600 states. They have given an estimate about states. It will take 600 states.
Huh? 600 steps for anything out there?
The estimate is 600 states per hour. 0 states per day. 102.5.
125.
No, 102.5.
100. DFT approximately. 100 calories for 600 steps. That must be right. 600, 10,000 will be over 1 point on the over. No, that is wrong. Because the 6,000 steps would be 1,000 calories. That's not. No, he says 600 steps are 100 calories. 6,000 will be 1,000 calories. And then 10,000 steps will be like 1,500 calories.
1 step means 30 centimeters.
About 70 centimeters.
20. 0.7 meters.
Yeah.
Divided with 0.7.
I don't know you calculate.
You easily calculate in kilometers then.
Ulta yaar. Today 70 centimeters is much easier. Everything till area of Lucknow. That's what you're doing.
70,000.
Take 67, 1.5 times. 100 centimeters, right? 1 meter is 1,000. 67 centimeters are 1,500. 67 times 1.5 is 100. Okay, so let's begin. All these are calculated because I run every day. I can beat some of you. All right. So she had a question. So let's just start with that. So when I'm writing, so your question is answered, right? It's delta E, not. Now, when I'm writing my energy like this, right? What I'm doing is, suppose you take hydrogen atom, right? Or any atom, or any homogeneous system. They're on now? Okay, let's turn this around. Okay, so in that case, I know the density is exponential, right? What I'm doing here, if you really make it slightly bigger, at each point, I'm taking this density to be like this. constant density. Right? So within this volume, I'm doing this. Next volume, I'm doing this. So it's an approximate. The kinetic energy or whatever is being calculated is approximate. So certainly, you can see that Ck, whatever it is, rho raised to 5/3 or dr cannot be equal to summation I pi I minus r del square pi I, because this is an exponential. It cannot be equal only if pi I is plane waves, right? So it's an approximate only for homogeneous. Exactly. Okay. So we've gotten the equation. Let's do that. If you could quickly calculate the function derivatives as I told you yesterday, you're going to get 5/3 Ck rho raised to 2/3, right? The plus B external R plus integration rho r prime over r minus r prime, right? Plus 4/3 Ck1, writing this x to minus of the Cx is positive, rho raised to 1/3 minus plus B, just write this B correlation is equal to. That's my equation for the density. Okay. Now something called Thomas Fermi approximation, which case I ignore all this and I write 5/3 Ck rho raised to 2/3 plus B external R plus integration rho r prime over r minus r prime dr prime equals mu. I'll go step by step. So this was the first equation that was proposed by Thomas and Fermi, right? Then I can do something more, because remember, since yesterday we've been saying that when you write the Hartree potential like this, you're doing taking care of there's self interaction in modern. So if I do something called the Fermi Marley correction, that is, if I subtract each electron's interaction with itself, and we'll do it because there's only density here. We can't really do with the orbital form. So what I'll do is, for each electron, I'll assume that the density is rho r by n. All right, 1 over r minus r prime dr prime, the minus sign, the Fermi-Marley correction. So in that case, with Fermi-Marley correction, this will become 5/3 Ck rho raised to 2/3 plus B external r plus this in effect becomes n minus 1 over n Hartree. Okay, with the Fermi-Marley. This is my Thomas Fermi equation for the density. How do I solve this? This is how do I solve? B external is given, right? And del square the Hartree is equal to minus what? Or 4 pi. No, over so not. So that will be minus 4 pi. With that, you solve this and you get your answer. We'll get to that, but before that, I want to spend some time on mu. What does mu mean? Okay. These are all C's for 2DFT. Okay. Mu. I'm claiming this chemical potential. Although it was introduced as Lagrange multiplier, just like epsilon I is in Hartree theory was introduced like Lagrange multiplier, right? But they had a removal energy thing, interpretation, use chemical potential. Why? Delta E, delta rho, R is mu, right? Now, once I have defined a functional derivative, okay? Once I define a functional derivative, it's in general true. So, even if I take delta rho R such that this is equal to some delta N, suppose I take a fixed derivation, add or subtract some, then delta E would be equal to, by definition, delta E delta rho R dr, which is mu delta N, right? So mu is d N, and that by definition is chemical. Any questions so far? Now, you may also ask, what does this having this constant achieve? You see, you have it like this. What you have, suppose I have an inhomogeneous system, some density like this. This is rho R. What we are saying, this term, which actually is the kinetic energy locally of the uppermost electron, the highest level, and that's what it comes out to be, plus V external R plus all the other terms is equal to constant. So what it means is that this condition arises from minimization of the energy. This means this constancy is required for minimization. Suppose this was not a constant. So suppose mu was a function of R. It was like this. This. This fellow, this is a constant transfer here. Delta E by delta N, that we have said mu is this. This energy will get lowered, this will get higher. Lower the energy. Until the constant, no matter how we transfer the energy, it remains constant. Remember, delta E will be 0. If mu becomes constant and mu is this, then if I transfer some electron from here to here, energy doesn't change. So this being constant means I'm really minimizing. Right? Now what will exact mu be? Now this is you see, chemical potential comes usually in terms of thermodynamic limit. That means changes are continuous. Well, what does it mean for, say, atom or a molecule or something? So let's look at that. What does mu mean? Oh, by the way, when you include this term also, it's known as Fermi. Let me write this. Thomas Fermi Dirac. Dirac introduced this term. There's 5/3 pk rho raised to 2/3 plus V external plus V Hartree plus V exchange, which is this term.
What is CX?
CX is some constant, some 3/4 something. Exchange. Okay, now suppose I have a system in which if I remove an electron, delta n equals -1, energy goes up, En plus energy. If I add an electron, delta n equals +1, energy goes down, En minus the electron infinity, right? I cannot do it fractionally. So mu is equal to minus I for delta n equals -1, that means you're removing the electron, minus A for so mu changes discontinuously. It's a small finite system, it's not dynamic, right? You average is equal to minus I plus A. Alright? Then I'll show you that how this minimization argument which I gave you was applied in terms of this I and A by Millikan. This is the electronegativity by given by Millikan. Not Millikan, Millikan. Okay. So although in Thomas form it will not come out to be I and A, but if I were to do an exact calculation, right? So exact from experiments, this is what you get. Okay, so from density, to define terms of density, this kind of is giving you an idea about this. Come back to this when I do E exactly. But the Millikan's argument is this. Suppose I have two systems, right? I have system 1, S1, system 2, S2. This has ionization potential 1 and affinity 1. This has ionization potential 2 and affinity A2. Then, if their electronegativities are the same, it should not matter whether I transfer energy from 1 to 2 or 2 to 1. Electron should not have any preferential direction to a transfer, right? So, if I is the same, then I should have I1 minus A2. I spend energy I1, gain energy A2. It should not be different from I2 minus A1. Why? Whether I transfer electron this way or this way, I should spend the same energy and therefore it should not really matter. And this implies minus I2 plus A2 equals minus. And when two electrons don't get transferred, then the electronegativities are the same. So, for a given system, this is what I do. So, if I can, one advantage I got by doing in terms of density is that I could get justify theoretically what electronegativity means. Otherwise, there are scales. Pauling gave one scale, Millikan gave one scale. This is how I'm saying I'm deriving. Alright, so that's inside. But keep this in mind. This is what happens.
Sir, when you are equalizing both sides, then you should write I1 minus A1 equal to
Right? How much energy do I spend if I transfer an electron from 1 to 2?
Okay. Then I1.
That should be equal to if I transfer the other way, if the electronegativity is the same.
That would be plastic.
Huh?
Mu, when you are defining mu,
So Part2 is for the average. I mean, 2 doesn't matter. I can write a factor next.
so there when you are defining mu, just minus I for delta n is minus I.
Is that what you? Yeah. No, because signs are different. That's why I got a minus. Okay. So that's that. Now let's come to Thomas Fermi. How good it is. There's been a lot of work on Thomas Fermi and still used because you see, if you have very dense system, then rho raised to 5 dominates. Other terms are relatively smaller. It becomes a good approximation. May not be good in atoms, molecules, but it's very good in neutron stars. Very good in where the density is almost the same. So I would, those who are interested, can go to the reviews of modern physics. By I think Larry Struck, if I'm not mistaken, just check this name. Early 90s. It talks about application of Thomas Fermi theory to stars, dense materials, plasmas, this and that. Lovely art. Okay, so check that. This is on Thomas Fermi theory. Okay, now this is all fine, but how good is it? He said we can may as well do approximate calculation in terms of density, but is it any good? So first things, if solve for atoms, then the density comes out to be zero at a certain point. Does not extend all the way to infinity. The reason being this: say you have some rho raised to 2/3 plus b external plus b hard 3 is equal to mu, right? As you go far away from the system, everything goes to zero. So mu is zero. Mu I can calculate anywhere. Mu is zero because as r tends to infinity, LHS goes to zero, right? If that goes to zero, you can see at a finite distance. Now, this is negative, this is positive, they'll cancel somewhere. So it goes to zero somewhere. Chemistry from outside, chemistry is all outside. Electrons outside region goes out. Number one. Number two, no shell structure. So density we should have, radial density we should have been something like this. You're getting some like this. There's no valence electrons, there's no conduction electrons. Again, a lot of solid state reaction atoms go out, the chemistry goes out. In that sense, also theory is not good. If mu is zero, this also implies I is zero. Right? So there's a problem. I've not done TDFT, that different story, but even there, a lot of work was done. I'll maybe come back to it more. Right now, I just want to take from here to TDFT. So there are these problems. But nonetheless, what it has shown you is that I can write something in terms of the density, solve it. At least I'm getting to a place where I can say what in the density, but there's something wrong with the density. Right? So that got people thinking. Question is, can rho r shown to be a variable using which can do exact calculations? That is the question at raised. So let's say, no, even if you ask the wrong question, it's okay. It leads to something. Wrong answers lead to something. But it raises more questions. It raises more questions, you try to answer that. You try to answer that, you come up with something. So it, you know, Bengali would say chuluni laga diya tha. Now what? Will you like again? Can we do that? And the answer is yes. Yes. And this is 2 by Hornberg function. This is Thomas Fermi is 1930s. This is 1965. So people were doing calculations, they were realizing somewhere it was good, then somebody it was good. Then they realized there's some problem, or somebody asked, let me do exact calculation. Right? And that gave us the whole EFT. Now, how do I prove this? So what we do is we say that this proved in a very funny way. Now that it's known, so it's not funny anymore. So we show that rho r ground state gives V external R unique. Alright? So now rho r, I've said ground state, I'll not keep writing it again and again. Rho r dr, I can gives me the number of electrons. And we are saying by Hornberg-Kohn theorem, rho r gives me V external. That means it gives me the Hamiltonian. Hamiltonian is summation I equals 1 through n minus 1/2 del I square, right? Plus, now, in principle, if I know the ground state density, I know V external. If I know n, I also know the Coulombic interaction. I know the n. So these two together imply this. And once I know the Hamiltonian, this implies I know psi. Ground state. If I know psi ground state, I know everything. So in principle, if I know the ground state density of the system, I can calculate everything. That's the point. Now, if I say, oh, this is a trivial statement, let's not. Let us look at the examples. Then I'll give you the proof. So, suppose I have one particle system. All right. In that case, the Hamiltonian is minus 1/2 del square plus V external. Right. H y equals E phi. That means minus 1/2 del square phi plus V external phi equals E phi, or V external phi R is equal to epsilon plus 1 over phi of del square phi. And for one electron system, phi is nothing but square root of rho. Right? Rho is pi square. Therefore, V external is epsilon plus 1 over root rho, 2 root rho. One electron system, given a density, I can make out what the potential is. Right? No problems with that. Two electron system, this is not okay. This is one electron, there is no interaction. Now, even in non-interacting system, suppose I have a 4 electron system. Then I'll have H equals minus 1/2 del square V external, and give me phi 1 and phi 2. Density would be 2 phi 1 R square plus phi2 r square mod square. How do I get the potential from it? Can you tell me something? Even if it is non-interactive. In the previous case, I could just invert the Schrodinger equation. How would I do that here? Can you find me mathematical speed? Huh? How do you do that? I've been given just rho r. Earlier case, when I was given rho r, I could just write the Schrodinger equation, invert it, and do it. How would I do it here?
Separate the two for sign.
Which two equations? I know only rho. I can write multiple 5 and 5. I can find an infinite number of two functions. They give me the same thing.
First, remove phi2 and solve for phi1, and then remove.
Okay, wait. So you're saying I take rho r. What do I do now?
You do phi1 square r.
Phi1 square r.
Then for the second part, we do rho r as phi2 square r. Then the linear superposition of both the values.
So I've taken this. What do I do next?
Rho r equal to phi2.
So this is something. I don't know this function.
Yes.
I don't know. No, I don't know the external. I know only this quantity.
Yes. And then again, rho r.
How do I know phi1?
In a previous case for one electron system, we have solved for 1 phi.
Yes, because there was only one orbital. The phi was root rho.
Here you do the same thing for rho phi1.
How do I solve for phi1? Huh? What is that? Start with? Yes, okay. So phi1. Yes. Okay.
Then phi2 is then
Phi2. Okay, so from this gives me phi2 equals square root of rho minus phi1 yes square. Then what do I do?
then same thing for phi2 is.
Phi2 I calculate for phi1. I can't
Okay.
guess it again.
And then you do the superposition of phi1 gas and phi2.
The self-consistent.
Huh? So I solve for minus r del square plus. So from phi2 I calculate p from phi2. Huh? Then get phi1 from here again. Keep doing it. Okay. That's one way of doing it. So something can be done, right? Now I have a wave function for two particles like r1, r2 is equal to, right? Let's say I just give it to you. Phi1 r1, phi2 r2 plus phi1 r2, phi1 r1. We wrote it yesterday for helium, right? Times 1 plus 0 point some constant phi, let's say, r1 minus r2 e raised to some b mod r1 minus r2. Right? Suppose I have this wave function. But I don't know this. All I know is the density. I know the density. Go on. This may be k. How would I find wave function from it? What is the potential? This I don't know. I know only this. So I'm supposed to determine A, B, 5, and 5. Anybody from outside? You can't. Then I'll keep increasing. I'll make it 4 particles, 10 particles. Can't. That's why this theorem is important. That in principle you can do it. So therefore I have to prove a mathematical theorem. Rho gives B external uniquely. Proof is very simple. Okay? And right now I'll assume non-degeneracy. There's only one unique ground state. So what do I have? Assume 2 B external, B1 and B2 can give same density. Assume that. Okay? Then I also know, so one Hamiltonian is B external 1. Hamiltonian 1 is kinetic energy operator plus B external 1 plus, let me write it B electron left interaction. Okay, that's 1 over R by A minus RT. And Hamiltonian 2 is T plus B external 2 plus B. And both, so one thing you should realize, this is very easy to prove, no common sign. If there are two different Hamiltonians with B external 1 and B external 2 differing by more than a constant, right? I should write that. B external 1 minus B external 2 is not a constant. It's a function. Then they'll have no common psi. I'll leave that for you. Very easy. Let's assume that they give the same density. Then the expectation value of H1 with respect to psi 1 is ground state. I'm going to use the variation principle and I'm assuming that gives the same density. And this is, I should write ground state. We are just talking about ground state because I'm using variation principle, so everything is for ground state. It's going to be strictly less than psi 2 H1. Psi 2. Okay? By variation principle, everything is ground state. This I can write as psi 2 H2 minus B external 2 plus B external 1 by 2. Right? From H2 I subtract this, add this, I get H1. This I can write as psi 2 H2, this is E2 plus B external 1 minus B external 2 rho R here. What does it assume? It assumes that B external is a local potential. That's all I'm assuming. Acts local. Okay? Now, once we do that, so what do I get? I get E1 is less than E2 plus integral B external 1 R minus B external 2 R. Since they give the same density, rho is the same. Right? I could have started with 2 here. I change this to 1, change this to 2, change this to 1, change this to 1, change this to 1, change this to 1, change this to 2, change this to 1, change this to 1, and put a minus sign. Then I would get E2. The left hand side I'll get E2, right? Is strictly less than E1 minus B external 1 minus B external 2. Both are functions of R. rho r here. Any questions on that? Just switch 1 and 2, it doesn't matter. Add E1 plus E2 is strictly less than E1 plus E2. So if I assume that two different potentials is differ by more than a constant, give the same density, iron into this power. It's like 5 less than 5. Right? So it cannot be. Applies V external 1 and V external 2 with the provision that they don't have they differ by more than a constant, cannot give the same density. And I'll write ground state. Because I'm working in terms of variation of principle, right? Top ground state. That's the one problem. You can also prove it for major case. I'll not get to that because the idea is that with density I can get. And as I said earlier, if I get the density B external, that means there's a 1-to-1 match between B external and ground state. This gives it unique to given a density in principle. How I do it is a different story. In principle, I can find this, and therefore size 0. And, so let's write Hamiltonian. In principle. How I do it will be a different story. That's the whole game. How do I use this here? Theorem by itself is a thing. Any questions over? Theorem just says that there is a functional relationship that exists. That means I can write rho 0 R as a functional of the external. It's a function of R. That means psi 0, R1, R2, all the way up to Rn can be written as functional of rho ground. R1. How I do it would give me the machinery, but the existence proof is there. And that means I can treat ground state density as let me make a very provocative but not really true statement. Rho R ground outside 0 is an equally good variable. As good as V external. After all, if I have V external, I get the system, right? V external and then of H. Any questions on this? How do I use this? This is used. So how do I use this fact? How do I make this useful to carry out calculations? So that's where variation of principle comes. Suppose I have a Hamiltonian and I calculate ground state energy. Since everything is determined by the external potential, this will be a unique functional. right? Keeping the same Hamiltonian, it will be slightly less than psi, some different one, same Hamiltonian, psi 1, right, by variation principle, right? Okay. Now, psi 1 corresponds to some density, some other density. So I have E rho 0, right? E rho 0, which is a function of the density. And the same functional, if I put a density which is slightly different, say rho bar 0, which will correspond to a psi 1, right? I have this equal to some E rho bar, right? So for the true ground state energy, ground state density, the energy is minimum. Is that point clear? I have an energy functional corresponding to this H. The same energy functional, if I put another density, which corresponds for this density, there will be another wave function. I can do this, give me higher energy, right? So E is minimum for true rho 0. That means delta E, which is functional derivative of E rho r, with the condition delta rho b n is a 0. That means delta E delta rho is equal to equation. I went quickly over to see I had spent a lot of time in Thomas Comey and all that. It follows exactly the same rule. All we have done is instead of writing that rho raised to 5/3, that, I'm just writing E rho. Everything else is the same. And by exactly the same definition, mu is the chemical potential. Mu is the chemical potential, and because now I've shown this is we are taking exactly, then the exact DFT will be minus I or minus A, or delta n equals -1 or delta n. And therefore DFT gives phi, which I have derived. All right. If I approximate E, one of the ways I can approximate E, which we said earlier is Thomas Fermi, which is an approximate calculation. Now we are saying we have proved E is a function of the density. Therefore, if I approximate E by that function, I get approximation, which we have already seen is not a very good approximation as far as chemistry is concerned. This is what it is. Any questions? Any question? Okay. Okay. So what we have established here, there is a unique relationship between ground state density and the Hamiltonian of the system. And for the true Hamiltonian, if I calculate the true wave function, right? Whatever way we calculate this, this will be less than the Same Hamiltonian, if you calculate this psi1 is a function of rho, so I can write this as some functional of rho tilde, right? I get it different. V external is being kept the same, so I'm going to put this V external, same V external. So I should put V external here. And Hamiltonian cannot change when I'm doing the variation, right? Are there any questions? And we have already seen approximate is Thomas-Fermi approximation, and that is not a good one. Now, isn't it still very useful? I'll show you where the usefulness comes. You see, now the question is this. When I calculated this, I actually calculated psi 0 E plus VEE psi 0 plus V external rho 0 R dr, and where I calculated psi 1 H psi 0, I calculated psi 1 E plus VEE psi 1 plus the same V external R rho 1 R dr, and this was greater than this, right? Because we kept the V external the same. Beauty is that these two functionals are these two operators, the T operator and VEE operator, do not depend on what system I'm talking about. Even a number of particles is the same, right? Therefore, whether I do it here, here, this has to be a functional of rho. This one is F calculated at rho 0. This has to be calculated at rho 1. Given a number of particles, this is a universal function. In fact, I don't even want to say given a number of particles because rho gives me n. So rho determines everything. So this is plus from V external R rho R here. Just one second. This is a functional which is universal. Universal in the sense it does not depend whether I'm talking about a molecule, whether I'm talking about an atom, whether I'm talking about solid, whether I'm talking about nucleus, whatever. Right? As long as that interaction is given, this is a function which is universal for a given interaction. And that makes it useful. If I can find that universal function as independent of the system, I can apply to any system. For example, if you look at the Thomas-Fermi kinetic energy expression, it was rho raised to 5/3. It's independent of what system I'm talking about. If you look at the Hartree term, that is independent of the system I'm talking about. So it's the unique universal function. Only thing I need is V external curve, and that's it. So equation for the density becomes delta F rho delta rho R plus the external R. Now,
So the functional is with kinetic energy plus V.
plus so expectation value is the kinetic energy and the electron.
And sorry, this psi 0 is
Wave function, the true ground state wave function,
and psi 1
is some other wave function,
some other.
which corresponds to density rho 1 or rho tilde, as I said. I wrote this rho tilde.
And that's variable, right? I mean, that's
Huh?
very.
I can take any rho I like. That was a true one. But the moment I take psi 1 corresponding to rho tilde, it will be greater than that. That's what gives you the variation of crystal density. That therefore, at the true density, it will be. Any other question? Any comments? Okay, so we have shown that there is an existence thing, that such a map exists, and then we have shown using that map, I can actually write the equation for the density. The only thing that remains for me to do is find F. Then we are done. Is that okay? All right. Now, if we write this explicitly, I want to spend some time on this. So, some parts I know for F rho, the expectation value with respect to psi of t plus PEE. So, this is going to be kinetic energy, which is also a function of rho. Psi is a function of rho, plus E heart rate, which I know, let me write this explicitly. I know this in terms of rho. Plus, I know already from Hartley-Fock theory and whatever we did in terms of wave function, there's going to be an exchange energy. I'm deliberately writing it separately, although you could have written it as exchange correlation. This is the energy. Oh, plus, that's it. This is that. Right? I know this. I don't know this. I don't know this. I don't know this. And we have already seen I can make some connection with T rho, right? And I get something which is chemistry wise or solids, conduction wise, valence conduction band wise, not. So that's that. There will be some other approximations. So there was a von Weizsäcker correction. So we have already seen. We've already seen T rho. And by the way, this is the kinetic energy for interacting side. It will be different from those in non-interacting systems. So we will come to that. But T rho, approximately we wrote as Ck rho raised to 5/3, which is not useful. And there's a von Weizsäcker correction you can make, which is 1/8 integral grad rho r square over rho r dr. This is to answer her question. I had earlier made a statement that this is like treating every part homogeneously. Now you're taking a little bit of first order waving also. Okay? So you can make those kind of corrections, but nonetheless, kinetic energy is poorly treated. And I need a better way of dealing with that. Then this part is left. So, for example, if you just look at the systems, and yesterday I had made this statement. If I look at any Coulombic system are usually bound by Coulomb potential. Ke, roughly, Ke of the sodium order of as E external, which are slightly larger than E heart rate, which is larger than E exchange correlation. This is usually the thing. Because remember, E exchange correlation is interaction of electron density with single charge. E heart rate is interaction of, these are all magnitudes I'm talking about. E heart rate is the interaction of n electrons with n electrons. So it is roughly 1 over n of this. And the external energy is much larger. Those are the ones that keep the system the same. So if I treat this better, that's the first priority. I should treat my kinetic energy better. How much better will come to later, but I'll give you an assignment problem right here first. Take this, you can do analytically. Take density or H-like atoms, ions. So hydrogen, helium plus, lithium 2 plus, and all that. And calculate the exact Ke, calculate the Thomas quantity, and see the difference. How much is the error? So numerically, I'm asking you to do that. But much more important, qualitatively, we saw it gives you good. So need to treat. Unless you do these calculations, you will not appreciate this statement that I'm making. Need to calculate, need to treat. Okay. Right. And that's where one chances. So what I'll do, just take 5 minutes short break, right? Then I'll finish one chance. I'll also write the equation that we talked about. 5 minute break, yeah? So this. Oh, what is that? Just need to say. Start at 10 to 1. वो ज़्यादा कम। In the meantime, you can ask questions. I'll go ahead. Sit like this. If you walk 600 steps, you spend 100 calories. This is a wrong calculation that I'm claiming. You're discussing that. Study them, the lectures in it, not that I want to lose weight.
Taking lecture also.
Because you put in everything into it. You just get drained out. Any questions from across the ocean, across the universe?
Online people,
So where are you from? You're all from SN boards? Different places?
ISCs,
ISC,
ISCs,
the association for
Israel,
SINB. Okay.
from here,
What you?
ISC.
Not you from ISC. ISC. So ISC is a bigger contingent. Let's have a match between ISC and SN boards. Oh, it's volleyball match. Huh?
and be happy that next time if you give everything early, we can arrange.
How much of this must be some overlap with the kind of lectures we had earlier? Cannot be that.
Lecture early.
So whatever coursework they do.
I think most of you have got registered for this workshop, right? Most of you are enjoying that. That's all. Very mobile man. It's a good workshop.
Maybe
Another
the
flavor of
deadline,
the
sorry, maybe the deadline,
Local. So tell me, how many of you are thinking of correlation really the way I brought it up? Really, I mean, I'm looking for feedback. Or was correlation just something that exists and what effects it has? But this is something I've worked on because I find a lot of people missing. Was it useful? Or you're indifferent?
Even in the books, they just the author just introduce the term in mathematical way. They don't give the physical content. They are
That's the point I was making. Was that's something which we find missing. I myself in learning, I found this missing. So one has to connect. This is for all the students too. Which don't just look at the book and take a term that you just give. Try to connect. We are after all doing physics. Right? It has to connect to whatever is happening in the real world. Like, try to do that, your insight becomes better. Read a lot. That's very important. Not just papers. Read about so many different perspectives. Pero it's what heavy. Okay. Now, given this, one more.
maybe it's the
The board.
and
B
one
and
is
A.
on the board also.
Huh?
Another one is
So this is the equation for the density. I've written this. Now let's say you come to treating kinetic energy better. How this is done is okay. Before that, let me write the this equation in full form: delta T, delta rho R plus V external R, right? Plus V Hartree R plus V exchange R plus V correlation R plus V. Where now, because of this functional derivative, anyway, functional derivative of Hartley also comes out rho r prime over that. That's known. The exchange potential now is defined as functional derivative Ex rho over delta rho. R correlation potential defined as delta E correlation delta rho R. The Hartley, of course, is delta Hartley or rho, but you know the expression. Now notice when I'm writing this, these two terms are supposed to take care of self-interaction. Okay? So if I approximate them, self-interaction may not be fully satisfied, but that's okay. It's one big comment. To go to Kohn-Sham system, we need to redefine something. Suppose, assume there exists a non-interacting system. So I'll call them just define non-interacting electrons. That means mass, everything is the same except charge is zero. So therefore muons also. Then moving in a potential some V, let's call it S, S for non-interacting. Okay? Then, and non-interacting can have the same density and has the same density as the interacting system. Is that okay? Am I violating Hornberg-Kohn theorem here? Because we claim that V external is uniquely determined. Now I'm saying there's another system. Am I violating Hornberg-Kohn? Yes, so two different potentials give the same density. Huh? No, that arrow was both ways.
That's true, right? I mean, because the total number of electrons are
Same.
So
No, change the interaction.
even if you're changing the interaction, it may redistribute, but total should be.
Yes, so what I'm saying is the Hornberg-Kohn theorem is never said, but it's that VEE was fixed. Now I made VEE 0. It's an entirely different system. Given interaction, V external is determined uniquely. So I can have two different potentials, the interaction is changed. I'm considering a different system. I'm not violating. This potential Vs would be unique for non-interactors. Cannot be two different. Okay. So now, if you do that, the corresponding equation would be delta T over delta rho. There's no VEE plus Vs rho, and density is the same, equals some mu.
What kind of potential is it?
Some potential, some non-interacting system. VEE is 0. But it will be unique, ground state unique. Okay? Some other mu. Let's call it mu bar. ES is non-interacting kinetic energy for same density. That's why I was writing T here and TS here. Okay, they need not be the same. Because what is T? TS rho. Non-interacting has phi's. So it will be phi I, just like RT. Whereas T is integration. Psi summed over I minus half del I square. Psi, right? And these two need not be the same. Although summation I, phi I R mod square is rho R, and so is this mod psi square R1 equals R, R2 R, and PR2 to PRN also rho. The densities are the same, but that doesn't mean the other expectation values will be the same, right? So both are different. All right? Any questions so far? So I'm just assuming there is a non-interacting system. Now we'll see that it does is that. Now I'm going to do something else. I'm going to write. So this is equivalent to solving minus f del square plus VSR phi I equals epsilon I phi I R mod square sum rho I. Everything is consistent, right? because the non-interacting systems are solving either that or this, they are equivalent. Now let me do a trick. Let me write this kinetic energy T rho as ES rho for the same density plus some T due to correlation. That's going to be the difference between the two. Whatever TC is, right? And write this equation as delta TS rho over delta rho, oh no, before that. Define E XC DFT to be EXC, whatever that was, plus EC. So exchange correlation in DFT is going to be slightly different from exchange correlation calculated from the expectation value. So it has that kind of difference. And this it takes care of all the many-body effects. Remember, EX arises from many-body effect, C arises from many-body effect. This is a many-body effect. This takes care of all the many. So then I can write that equation as delta TS by delta rho, right? Plus V external R plus V Hartree R, density is the same, plus Vx C, let's write this. And this is from DFT. R equals mu, where Vxc R is delta EXC DFT over delta. All right? So they're slightly different. In fact, since I'm writing Vxc here, let me write this Vxc out here as quantum chemistry. Quantum chemistry. This will be DFT. This is quantum chemistry. Quantum chemistry. This is DFT, so I'll remove DFT. Now that is clear. So now whenever I write EXC, it will mean this equation is equivalent to this. It's exactly the same structure, right? That means this is equivalent solving minus 1/2 L square plus V external R plus V Hartree plus VXCR YI plus epsilon I YI. Okay? These are all local potential. Summation phi I square gives me rho R, and ES rho is equal to summation I minus 1/2 L square phi I. Okay? This is the constant. This has to be solved self-consistently because I'll start with an approximate phi I, calculate the density. From that density, I'll get the potential V Hartree, V exchange correlation. Everything else is given. I'll solve, see if the potential is the orbitals coming out are the same, and go again until they become the same. So to be solved self-consistent. Self-consistent. It's not correct in this, so let me write self-consistent. Is that point clear? Right? So we've gone back to orbitals. All that density hoopla we did, we've gone back to orbitals. Nonetheless, it's much easier to solve than Hartree-Fock. What was the potential in Hartree-Fock? Non-local. Here everything is local. Multiplicative. right? And this is known as Kohn-Sham potential. Exchange coordination potential, Hartley potential, external potential. This is known. This can be calculated from density. This only this has to be approximated. Only approximation we need. That is the price you're paying, right? You can do much larger system than conventional quantum system. Still, the charm is for density, but we will come to that. Now, once you solve it, you get your density. You put it back in the exchange. This functional kinetic energy you're calculating exactly, non-interacting kinetic energy. Rest whatever you're approximating. So let me write this only EFC rho, and therefore this. Therefore, VXC has to be approximated. So you calculate the density, put it in the energy functional, and you get your answer. That's the problem. You can vary different parameters, calculate the frequency and all that. Now, a few things. By construction, you see this and the original equation is the same. So mu on sham is equal to mu 2. Agreed? Because from that exact equation I made this. So if I could solve it exactly, they should be the same. That, and what is mu on sham? What will be the minimum energy required to remove an electron? E uppermost. This is my Kohn-Sham system. Once I have solved it, this is the Kohn-Sham system. Phi 1, phi 2, phi 3, so on, phi max. This is my non-interacting system. Mu would be the minimum energy. This is easier. This would be mu. So mu is equal to epsilon max Kohn-Sham. Therefore, this would be answer. Any other orbital has no mean. All you have made is a system which gives you the correct density, which gives you the not correct corresponding non-interacting kinetic energy. You solve it approximately, these are also slightly approximate. In the exact sense, this is what it should be. So it not only gives you the energy and the density correctly, if solved in exact form, it gives you the ionization. Is that okay? You can also show what is known as Dennis theorem. Although calculating only the ground state, but suppose I vary the occupation number of IF orbital comes out to be okay. That energy doesn't mean anything if once you have removed the changing the say if you're changing the occupation number here or here because you're no longer in ground state. Nonetheless, it's an interesting here. But if you're removing only from the top, then you remain in the ground state. In that case, this becomes E max and that is EI. So this is known as the ionization potential. Okay. So this is the Kohn-Sham setup. Now on the side, I also because now we are exploring many things, so you can do many more electrons, but still being able to solve the problem in a orbital free way would be very interesting. Can I make that? Suppose yes.
Can you take the quantum that is film consistently or
No. EXC quantum chemical, if you have the exact wave function, if I take the expectation value of VEE, that will give me a Hartley term, and whatever is left is the exchange term. But that is quantum chemical.
and DC coming?
DC is coming because the kinetic energy of kinetic energy is What is this? This is the true wave function, kinetic energy operator for an electron psi. What is this? This is some corresponding phi I minus half del square phi I summed over I. They need not be equal. The wave functions are different, so this is right. Anything else? Now you can also write the different forms of this. So suppose I write Ts rho as I told you about one Weizsäcker term, del rho square over rho, and I'll add a term to this which I'll call T Pauli. Let's give you why I'm saying this. If all the electrons were in the same orbital, this is like the bosonic kinetic energy. Whatever is left is the because of Pauli principle. If you write it like that, you can transform this equation into an equation for the density, and that comes out to be like this: minus 1 half del square plus V Pauli, which will be the function derivative of this, plus V external plus V Hartree plus V exchange correlation square root of rho equals mu of square. And for this, there's an expression. So this is I'll call some V effective. There exists an expression in terms of psi. An expression in terms of exact psi exists. It's a long expression. So if I can make that V effective some approximation for that, some approximation for V Pauli, I also have a Schrodinger-like equation for square root of rho. In principle, if I know psi, I need not solve this. But this gives you a lot of way of exploring DFT and DFT wave function connection. Okay, this is one area where we ought to go. Because now computer power is increasing, I can mix the two. I cannot still go fully interacting wave function, but this is used in many, many different ways. So this expression is, you actually define the density amplitude by n minus 1 by taking square root of rho r over n psi n r1 r2 to rn, and then you work out things in the Schrodinger equation and you get an expression. Because of this, we get a term which is half del square. So this is one area which can be used to study. So one is this practical aspect. You make approximation for VXC, you make approximation for EXC, and we do the practical calculation and come out. Other is how far can I push the theory? How can I make it better and better? Things like these actually help. This is going to be a new area of exploration. We have used some of this in many, many things. All right. There's something some of you may know. So this is Conshan. How to solve it? I'll do the LDA part and some other exact properties tomorrow. I'm now dead.
Okay. One photo.
Why also standing?
Yeah.
So shirt gets you the picture. Instead of doing t-shirts. Yeah. After the mass,
I'll give you a call. I think this year signed, probably she has sent or oh, really? Okay, okay. I'm just
अरे एक फोटो खिंचवा लो। जल्दी ना मतलब खराब मत करना।
Thank you. So again, tomorrow at 10.